So last time, so we discussed these critical section problem using the semaphores. Uh, the semaphore solution is based on two operations. Okay, you can interpret these as two functions. One is the function v, the other one is function p, and there's a integer type, and we call this integer a semaphore. Okay, I use s over here in the definition. So the semaphore is an integer, and typically we we can initialize this semaphore into one. Okay, so initialize to one. So then for every process, P1, P2, P3, and here's a PI, and all the way to Pn. So we have a 1, 2, 3, 4 I n. We're supposed to have n processes. Each process has its own critical section. Now, these critical, I put the SCS. It's not just one statement. It's basically the CS is a block of instructions. Now, this block of instructions is going to be the instruction that going to access the shared variable among all these processes. Okay, so the CS for P1, the critical section for P1, may not be the same instructions as the critical section for PI in this case. So it just says that this critical section is the fragment of instruction that they're going to access the shared variable. Or share the data. Now, it could be like if I have a shared variable like value A. So this critical section for P1 may just access the value A and just read the value A. Okay. Now, this critical section may actually write the data to variable A. So somehow these critical sections are basically accessing the shared variables. Now, the critical section problem is as we mentioned in the last as we mentioned last week, that the critical section is basically a piece of code that accesses a shared variable, and we have 5 conditions, 5 requirements. One is the mutual exclusion, right? So that means if we have n processes, or each has its own shared critical section, and the number one condition is in any particular time, only one process can enter its critical section. Okay, so you cannot, you should not allow multiple processes in their critical section. Only one is allowed. And then also we talk about, if a process is not in critical section, it should not block other process to enter its critical section. And also there's some other condition says if a process is tried to enter its critical section, the process should not wait forever to enter its critical section. That means it should not be blocked by other process forever. There's another condition, I could not recall that, but there are 4 conditions. Okay, I think the mutex is the most important one. The other, conditions, let's just try to guarantee that there's no starvation, no deadlock, something like this. Now here's the implementation for the critical section problem using semaphore. We defined 2 operations. One operation, V, is pretty simple. It's just to actually update the semaphore. The semaphore is also a variable that's shared by all the processes. So the V actually gonna just increment the semaphore. Okay. And then another operation P is also applied to the semaphore, but in this case, P gonna actually decrement the semaphore. But before P can actually decrement the semaphore, you have to check whether the current value of semaphore is less than or equal to 0. If it's less than or equal to 0, then you should not actually enter this operation. So this while loop basically is a while actually statement with empty body. So that means if this condition is true, then this P will be stuck over here, stuck in this loop, never going to be able to pass the while loop. So if this condition is not true, then it will actually skip the while loop and enter the next one. Okay. Just let me know if you have any questions on this before we move forward, because that's very important. So now, here is the implementation. So we can actually implement the 2 operations P and V this way. It's basically the same implementation for all processes. Now, once we define the critical section for each of the process, you just need to put this P operation before the critical section and the V operation after the critical section. Same thing here. Okay. Now, in this case, the semaphore, the name of the semaphore is called a mutex. Mutex is actually a kind of like an acronym which basically means mutual exclusion. Okay, it's a mutual exclusion. So they put the MUT from mutual and EX from exclusion, and they put together as a one word. So it's a mutual exclusion. So this mutex is the semaphore now, and which is initially assigned 1 to it. Now, let's take a look at the scenario. When P1 try to enter its critical section, so before P1 enter the critical section, it will first call the operation P, and with the argument of mutex. Okay, so suppose that P1 is the first process that wants to enter the critical section. If it's the first process wants to enter the critical section. Now, what is the value of mutex? It is 1, right? So the mutex is 1, and then P1 actually calls the operation P with mutex 1. So then P1 is called, the mutex 1 is passed to the parameter S as a pointer. So S is actually pointing to the mutex. It's a pointer. So this is actually, it's a pseudo-tag. It's a pseudocode, but it looks like a C language or C++ language. So that's why most of the syntax basically simulated to C language. So now S is 1 because S points to the mutex. So now we check the while loop. So this is 1. And we compare 1 with 0. 1 less than or equal to 0. That's certainly not true, right? 1 is definitely greater than 0. So if this is not true, so we skip the while loop and go to the next statement, s minus minus. So the value of s is reduced to 0 because initial value of x is passed is 1. So s minus minus so is reduced the value to 0. This actually in turn reduced the mutex to 0 because s is a pointer to the mutex. So that's why we change the value of mutex to 0. And then P1 is in the critical section now. P1 get a chance to enter the critical section. Now, let's talk about something else. While P1 is in the critical section, and suddenly another process, let's say PI, wants to enter the critical section because they are running in parallel, right? Either by using multiple CPUs or using one CPU but use the time sharing, so they switch back and forth. But they're running in concurrently. So if PI wants to enter the critical section, so again, just like a P1, PI gonna actually call the operation P. So now at this time, remember the mutex is 0, right? Because it was changed by P1. So when PI calls the operation P with the mutex 0, so S is also a pointer. It's pointer to the mutex. So it is 0. So then you check the while loop. It's 0. 0 less than or equal to 0. Yes, 0 is equal to 0, right? So of course it's less than or equal to 0. So the condition is true. And then you're going to execute the body of the while loop, but there's no operation in the while loop. While loop is an empty loop. So, but you're going to actually it stays in a while loop. Never going to get a chance to pass the while loop. So it's actually stuck over here. So PI going to be stuck over P. So it's actually going to continue to run the while loop. So it check the value of S is 0. So then again, it checked the value of S, it's 0, and it doesn't do anything, just an empty loop. And then check the S value, check the S value, check the S value. And why, as far as the value of S is, the value of mutex is still 0, then it will continue to actually run the while loop. Now, when this while loop will be broken, it's up to the process 1, right? Process 1 is currently in the critical section, and it continues to run a critical section, and then it's done with the critical section. So once the process 1 complete its critical section, and then it will call the operation V. Now, operation V at this moment, because mutex 0, it was changed by P1, right? It was changed here. So now, when V is called with a mutex 0, mutex value 0, so then the value of mutex can be incremented. Okay. So S, the mutex becomes 1. It's incremented. So once it passed the V, okay, then the mutex value will be changed back to 1, right? Since these processes are running concurrently, so this process 1 changed the value of mutex from 0 back to 1 after it completes the critical section. And while the process I is continue to check the while loop, and suddenly, right after process 1 change the mutex value 1, it's reflected over here. And then suddenly, this process I find out, wow, the value is 1 now. Okay, so now the condition is not true anymore. So then process I going to be able to execute the S minus minus and change the value of mutex to 0 again. So now the mutex is back to 0. It's back to 0. So that means at this moment, process I is in the critical section. Now, it doesn't matter how many other processes want to enter the critical section at this moment. They all will be stuck, right? If other process try to enter the mutex, it's just like the first actually process 1. So this basically guarantees that only one process going to be able to enter its critical section. So that's the semaphore solution, using the semaphores to solve these critical section problems.
Dr. Chen.
Yes.
Is it possible in a scenario like this for the value of mutex to be anything other than 0 or 1?
It is possible, because depend on how we're going to use this semaphore. But this is actually, we try to use the semaphore to solve the critical section problems. So that way, we initialize the semaphore to 1. There's other scenario that we try to solve some other problem. Then the semaphore value could be something else. Yes. So this operation V and P, just to actually, there are two actually, it's called atomic operation. That means the operation P and V are not separable. Once you actually enter the P, you cannot switch away. So you have to complete all the operation in P. But once you use the V and the P2 operations to solve the semaphore problem, then you can set up the semaphore to 1. But there's some other actually approach. We're going to actually see some other examples, like the consumer and the producer problem. Remember the consumer and producer problem, right? So if we try to solve the other problem, producer and consumer problem, with more than one slot in the warehouse, then you can use these two operations. But in this case, we're going to use two semaphores. Okay, so let's actually move forward to see the other problem. But for the CS problem, the critical section problem, if we try to use the semaphores, we can solve this problem, using these semaphore. And in this case, the semaphore, the variable going to be set to 1. So this is going to allow only one process to enter the critical section. Now, you can think about this. What about if we set the semaphore, the mutex, initial value for the mutex, not to 1, but to 2? What do you think? Then in this setting, we will allow two processes to enter their critical sections, right? Because when one process try to enter the critical section, call the actual operation P, the P gonna actually reduce the mutex from 2 to 1. And then when another process try to enter the critical section, the mutex value is 1, not 0. So the other process can also enter the critical section. Then if we set the mutex value to 2, then we will simultaneously allow two processes to enter their critical sections, right? So the mutex is very important. The mutex value is very important. So because of this mutual exclusion requirements, so we have to set the mutex to 1 to solve this problem. Let's move to the next example. It's called a bounded buffer problem. Okay. So remember that we talked about the process, producer and the consumer problem. We assume that there's one shared data. Okay, it's you can interpret this as a warehouse, which can house one product. So the producer going to produce one product and put it in the warehouse and set the flag. Say, okay, the product, the buffer is full, and then the consumer going to actually check the buffer and check the flag. If the buffer is full, the consumer is going to consume the product and empty the warehouse. And then after consumer empty the buffer, it just set the flag down, right? Says now it's empty. And then the producer check the flag. If the flag is up, the producer is not going to actually load the next product into the warehouse, because the warehouse can only accommodate one data. Now, bounded buffer problem is actually it's a very similar to the producer and the consumer problem, but at this time we have some certain limit. Okay, so the bounded buffer problem is a classical synchronization problem intended to illustrate the process cooperation. Okay, a producer, in this case, producer process share a buffer with consumer process. Okay, it's still a consumer and a producer problem, but now the buffer has fixed the number of slots. So the buffer has fixed the number of slots instead of only one slot. So in this case, we're supposed to have n slots. Okay. So that means I can produce n, I can produce a quantity of n products. So I can put each of the product in a slot. Okay. So now, so here the producer fills empty slot with data in increasing order. And the consumer actually follows the producer by removing the data in the same order. Okay. So the buffer is called a circular buffer, because the producer going to produce the item, say, okay, I produce a product, a data, I put in the buffer, and put in the buffer, put in the buffer, put in the buffer, put in the buffer, and then the producer actually put the product into the buffer, and then the consumer actually follows the producer and remove the product off the buffer. So producer keep actually going. Consumer actually follow the producer and remove the buffer, and the producer keep going, and producer actually produce a product and put it in the last, slot. Okay. Now, if every slot is filled with the data, then the buffer is full, right? So every slot has the data. The buffer is full. But however, because the consumer is actually following the producer, so the consumer going to consume the product. Every time one consumer consumes the product from here, 0, and then it's just remove the data off the buffer. So this buffer slot is empty now. It's free. And then it just remove the next one, and this one is free. And then remove the next one, this one's free. So the consumer should follow the producer. Okay. So when producer actually, fill up the next slot, you're gonna go back and start over again and fill up the slot again from the beginning. And once it's complete, and they just start over again. As far as, so you can interpret this buffer just like this, a circle. You can interpret this as a circle, right? So this is actually slot 0, 1, 2, 3, 4, 5, and the last one is n-1. So the producer just keep actually fill the product, and the consumer just follow the producer, chase the producer, and empty the slot. So it's just like a two processes. One just try to put the stuff in there, and the other one follow that one and try to remove the stuff out of this buffer. So if you interpret this as a circular buffer, then you're going to say producer is actually probably somewhere in slot 4, right? And the consumer is actually probably follow it over here in slot 1. Okay. So because it's a circular buffer, it's really hard to say which one chase which one. You can say consumer is chasing the producer, or producer is chasing the consumer. So either way. Now, the problem is, in this kind of problem, so if the producer actually produces the data and fill the slot faster than the consumer can consume the data, so sooner or later, the speed of producer is faster than the speed of consumer. Or sooner or later, the producer going to actually eventually catch the consumer. So that means all the slots are going to be full, right? Or on the other hand, if producers keep going, but it's slower than the consumer, so then consumer keep empty the slot, and producers actually fill the slot, but consumer is faster than the producer. So that means, then in this case, sooner or later, all the slots are going to be empty. So this is just like you can interpret this like a warehouse problem. So when we talk about like a Walmart or Kmart, we will talk about inventory problem. So here's the warehouse, okay? So the producer, the vendor, keep actually produce the product and ship to the warehouse, fill in the warehouse. The warehouse has 100 slot, for example, or 1,000 slot, whatever it is, okay? So it's just keep filling. And then if the producer actually fill in the slot much faster than the consumer can consume the slot, then sooner or later, warehouse is going to be full, right? So this basically simulates some kind of a business, like when the economy is not so good, so the producer produce more products, and they cannot sell much of the product, so the consumer cannot consume that much, product at the same speed. Then the producer going to actually, sooner or later, producer going to fill up the warehouse. The warehouse is full, so the producer cannot fill more actual, product into the warehouse. And if the business is so good, the economy is so good, people are just buying stuff, so the consumer can consume the product faster than the producer can produce. In that case, the demand is higher than supply, right? You can interpret producer as a supply, the consumer as demand. If the demand is much higher than supply, then the warehouse tends to be empty. If the demand is lower than the supply, so you supply the product faster than the consumer can consume, then warehouse is going to be full. Okay, so this is actually kind of like a more like a business problem. Okay, so in most of business, when people actually try to build a warehouse, the issue is how big the warehouse should I build? Okay, if the warehouse is too big, then you have to actually invest more monies on the real estate, because you have to build a big warehouse. In that case, you have more buffer space. Now, typically the business just try to find a balance. They try to actually make sure the producer and the consumer are going to actually work in a nice way, that the producer never going to stop producing, and consumer never going to stop wait for the producer to produce. So then they need to build a size of the buffer to make the business run smoothly. Okay, if the warehouse is too small, then it might be, the buffer going to be empty very quickly. Or if the buffer is too big, it works fine, but it costs you more money. So that's actually the issue. Now let's take a look at this kind of problem, the bounded buffer problem. So now we have a producer and a consumer problem in this case. But in this case, we have the warehouse as n slot. So from 0, 1 to n minus 1. If we have n slots, then the first slot is 0, the last one will be n minus 1 because we start from 0. How to resolve this problem using the bounded buffer problem using semaphore. Now let's talk about this. So we're going to still use these two operations, V and P. Okay. However, we're gonna create two semaphores. One is called E. The other semaphore is called F. We have an F and an E. Okay. The semaphore F represents the number of full buffer slot. Okay. So the semaphore F represents the number of full buffer slot, and the semaphore E represents the number of empty slot. Okay. So now if we talk about this buffer, so let's say, again, I like to draw this circular way. Okay. So this is the first slot, 0, 1, 2, and this is a n minus 1. That's the last one. So you're going to actually 3 going in a circular way. So we always just guarantee that the F plus E going to be, what is the value of F plus E?
Like the total number of slots.
Yeah.
Total number of slot, which is n, right? Because F represents the number of full buffer slot, and the E is the empty buffer slot. But so if half of these buffer slot is full, half of this buffer slot is empty, then so that means if that means the warehouse is half full. Okay. Now, how this actually semaphore F and E gonna work in this bounded buffer problem? So this is actually more general problem. It's not the consumer and the producer just to work on one slot. We're working on n slot. Now let's take a look. Okay. So initially, before both the producer and the consumer start to run, so we can assume that all the buffer slots are empty, right? So that means F is 0. So the F represents number of full buffer slot. So initially, all the buffer is empty. So F is 0. And E is n. Okay. Now, here, we can actually call. So this is actually the critical section. Basically means that the producer going to produce the product and put in the buffer. So because the buffer is a shared area, buffer is shared area, right? It's shared. So every actually code that are going to access the buffer is the critical section. And the consumer remove the data from the buffer. So that's the critical section for consumer. Okay. Now, instead of using the flag, remember the flag, using just the producer actually fill the buffer and set the flag up. And the consumer actually remove the product and put the flag down, right? Now we need 2 flags because we have n space. These 2 flags is the semaphore, F and E. Okay. So now when producer try to enter its critical section, that means producer want to produce a product. So initially it's empty, the buffer is empty, and So F is 0, E is N. Okay. So the producer gonna call the operation P. Okay, with the semaphore E. So when producer actually so initially the value of E is N, right? E is N. So that means the N will be passed to S. So this is N. So N, let's say N equals 10. Okay, just use the actual number. So initially the value of N is 10, and the 10 less than or equal to 0. Of course, that's not true. So I can decrement the value. So now the value of E gonna be decremented to 9, right? So the value of E becomes 9. So then producer basically produce the product and place in the first slot. Okay, and then when the producer finish the operation, it's gonna call another operation V. But in this case, the value of V gonna apply to the semaphore F. So because V gonna increment the value, so that means F is initially 0, but now the value of F becomes 1. Okay. So E becomes 9, F becomes 1. So we are balanced. E plus F is still, F plus E is still 10, right? So now let's say, suppose the consumer hasn't started to consume the product yet, and the producer going to continue to run and produce the item. So the produce P operation is called again. Now this time, because now F is 1, right? E is 9 now. Okay, and then it's just called operation P applied to the semaphore E, which is 9. So 9 is still less than or equal to 9 less than or equal to 0. That's still not true. So it's going to continue to actually decrement the value of E to 8. Okay. So the value of E becomes 8. And then after you place the item in the buffer, the F going to be incremented, right? Every time when I call V, the value of F is incremented. So the value of E and F, basically, every time when produce item, it just decrease the value of E and increase the value of F. So you can imagine that if the producer actually runs like 10 times, sooner or later, the value of E becomes 0 and the F becomes 10. That means the buffer is completely full, right? Now, in the meantime, because this is actually kind of like a dynamic operation, so it's not always the case the producer is running. The consumer also going to run somewhere, right? Sometimes, right? So every time a consumer is running, the consumer going to actually decrease the value of F, because the consumer going to every time consumes an item, so the number of full buffer slots going to be reduced by 1, right? Every time consumer consumes the item, the number of actually full buffer slots going to be reduced by 1, and the number of empty slots can be increased by 1. So the producer can actually increase the semaphore F, or increase the semaphore F, or decrease the semaphore E, and the consumer going to actually, increase the semaphore E and decrease semaphore F. So each producer and the consumer going to actually just change the values F and E in the opposite way. But we still want to make sure that when producer is producing anything, it should make sure that the semaphore actually E is still not 0, right? Because semaphore E represents a number of empty slots. So as far as there's still empty slot, the producer can enter its critical section and produce more items. Okay. So this is actually the bounded buffer problem using semaphore. Okay. Now in this case, now unlike these critical section problem, we have all the process shared one actually semaphore, and we use the name called mutex. But in this case, in the bounded actually problem, then we use two semaphores. Make sense to you? Okay, I'm gonna move forward. So if you have any questions, just stop me. Okay, interrupt me. Now let's actually discuss another problem that's called classical synchronization problems. There are a couple of actually classical synchronization problems. If you read the Xi books, there's a read and write problem. This Dino philosophy problems is another classical problem. Now, people create all these classical synchronization problems just basically used to test any kind of approach in the operating system design. When they design the operating system and they want to make sure the operating system going to be working correctly when dealing with multiple processes, particularly in this case, the scheduler. So when they're actually working to collaborate among these, these processes, they typically use the classical synchronization problems. Now, the dynamic philosophy problem is actually it's a very simple problem. Okay. So in dynamic philosophy, you have 5 philosophers. Okay. And they are ancient Greek philosophy. They are very smart. They think about the important problems. Okay. Now, these philosophy each, each represent a concurrent process. So that means 5 philosophers represent 5 processes. Okay. Now these 5 philosophers, they are seated around a table, and then there are 5 forks, each representing a resource. Okay. So it's a round table. You have 5 philosophers, and then you have 5 forks. Okay, between 2 philosophers there's a fork, and here there's a fork. There are 5 forks. Okay, now each represent a resource. These 5 forks placed on the table such that each two neighboring philosophers share 1 fork. Okay. Now each philosopher alternates asynchronously between a phase of thinking, which represent excusing not requiring any shared resources, and the eating. So these philosophers, they just do 2 things. One is thinking. The other one is eating. So they just do 2 things, When a philosopher is thinking, the philosopher is not eating. So that means the philosopher is actually sitting there and without using any fork. Okay. So when the philosopher stops thinking and wants to enter the phase of eating. Okay. When the philosopher feel hungry and say, I cannot think, but then I want to eat. So then the philosopher need to pick up 2 forks. Okay. So each philosopher, if he wants to eat or she wants to eat, the philosopher need to pick up 2 forks. Okay. You need to pick up 2 forks, then start to eat. Now that's the dining philosophy problem. So what's the issue with this dining philosophy problem? So here's the main challenge. So the main challenge is you want to make sure if a philosopher wants to eat, the philosopher can get these 2 forks around him or her. Okay, that's the main challenge. Now, if we don't set up any actual rule for this, there's a probability that the starvation may actually happens. Okay, or even worse, they may enter some kind of deadlock. Okay, the starvation may happen because one philosopher wants to eat, and every time one philosopher wants to eat, then there's always actually a neighboring philosopher who is eating. So that means if the neighboring philosopher is eating, that means one of the fork is not available. So then the philosopher cannot eat. Okay. So that's the dining philosophy problem. Okay. So let's say philosopher 0 is thinking, and the philosopher 4 is eating. So that means the philosopher 4 has 2 forks, right? So in this case, if philosopher 4 is eating, then philosopher 3 and the 0 cannot eat because these 2 forks are not available. So that means philosopher 3 can only get 1 fork, and the philosopher 0 can only get 1 fork, not this one, not this one. So that's the problem. Now here's some kind of thinking. Is there any chance that the deadlock may happen? Is there any chance that the deadlock may happen? So let's say if philosopher 2 wants to eat, the philosopher 2 just look around, look at the left, say, oh, this fork is available, so I grab it. Okay. And then look at the right, and this fork is available, and grab it, right? But if this fork is not available, so the philosopher 2 can request for the fork. But currently, the fork is in the hand of philosopher 3. And the philosopher 3 has the fork 3, but philosopher 3 requests for fork 4. The fork 4 is not available because fork 4 is currently in the hand of philosopher 4. So this is kind of like philosopher 3 has to wait for the fork 4. The philosopher 3 is holding the fork 3. And the philosopher 2 is requesting for fork 3 and holding the fork 2, right? Now, so there's some waiting, okay? But that's okay, right? Because philosopher 4 is eating. So at this time, the philosopher 4 is grabbing 2 forks. It's currently eating. Now, when philosopher 4 finish the eating and start to think, then philosopher 4 gonna release these 2 forks, and these forks can be free. And the philosopher 3 says, okay, the fork is available, so then it gonna actually grab the fork, and the philosopher 3 can eat, right? Now philosopher 3 has 2 forks, and once the philosopher 4 finished the eating, start to think, and then philosopher 4 gonna release both of the fork, and this fork becomes available. So now philosopher 2 can grab it. Okay, so each philosopher may need to wait to get to both actual forks. So the philosopher can grab one fork and waiting for the other, and grab the other fork and waiting for the other. Or philosopher can actually get both forks. Then the philosopher can eat. Now, what's the potential problem with this approach? If we actually don't set up any rule, what could happen? So problem is not how many philosophers want to eat. Okay. The problem is, or the problem is not in a philosopher is eating. If the philosopher is eating, that means the philosopher is holding both resources, holding both forks, and the philosopher is eating, right? Okay, so I see one from Kyle. All other philosophers can get locked out of eating when there are enough forks for at least two to eat at the given time. Okay. Yeah, that's true because there are a total of 5 forks.
So like, wouldn't deadlock occur if like each philosopher, I guess, like they pick up one fork and they have to like request another one? Like each one picks up one fork and then they request the other, and then nobody would be able to eat, right?
That's true. However, there's some differences. One scenario is if we set a rule that each philosopher, whoever wants to eat, they have to pick up the left fork first and the right fork next. Now, in the extremely actual scenario, all actually 5 philosophers try to eat at the same time. So they both actually they all actually pick up the left one. Okay, they all pick up the left one. Say I pick up the left one and get the left one, and this guy pick up the left one and get left one. Get left one. And then they're waiting for the right one. So now we can find out each philosopher is holding his or her left fork and waiting for the right fork, right? So like the same scenario. So that is deadlock, right? Because no one can get the right one. And no one wants to actually release the left one because I'm holding the left one, I'm waiting for the right one. I'm hungry. So I'm holding the left one and waiting for the right one because I'm hungry. So I don't want to release the left one. So if all the philosophers just holding the left one and waiting for the right one, that's a problem, right? That's a deadlock situation. Now, but each one is waiting for a fork doesn't necessarily mean there's a deadlock. If we don't actually follow this rule, if one philosophy actually pick up the right one first and the left one second, and the other philosophy pick up the left one first and right one second, then you have some kind of situation that some philosopher may wait, but sooner or later one of the philosophers going to be able to eat. That's not a deadlock. You may actually have some delay, but there's no deadlock. The deadlock only happens when in this scenario. So when they each holding the left one and the request for the right one. Does that make sense? So let's actually take a look at the solutions we may actually implement. Okay. So the behavior of each philosopher PI can be represented as a loop that alternates between the phases of the thinking and the eating. And prior to eating, philosopher I requests the two adjacent forks, and return the forks when finished eating. The forks can be represented as 5 semaphores. So that's the solution we want to actually provide. Okay, so we have 5 semaphores because semaphores actually, they're shared. Okay, so these 5 fork semaphores are called F0 to F4, F0, F1, F2, F3, F4, and all initialized to 0, or initialized to 1. Okay, so now we can define these two operations P and V. Okay, P basically correspond to picking up the fork, and the V corresponding to putting down the fork. Because remember the P is the function that P is the operation that reduce the semaphore. Because initially all the semaphore is set to 1. Okay, so all the semaphore is set to 1 initially. Okay, let's forget about this. All the semaphore is set to 1. So when process 0 wants to actually eat, the process 0 actually grab the, so the process 1 gonna call, process 0 gonna call P, okay, process 0 gonna call P of F0, right? So you're gonna decrement the value of F to 0. Okay. Okay. So when F is 0, then process 2 wants to call PF0, then because F0 is already a 0. So it will be stuck. So you're picking up the fork can be represented using the operation P, right? And the release the fork, it can be represented using the V function, right? Okay. So this is actually a solution we have. For each P philosopher, it's an infinite loop. So we always use Y1, and then it just do the thinking. Here's the eating. Now thinking is okay because thinking doesn't require any resources, so it can do by its own. But only when the eating happens, you're going to actually access the shared variable. So you need to actually define the eating as a critical section, right? Thinking is not a critical section. Okay. So when process I try to enter the critical section, which is eating, then process I gonna grab two actually forks. One is Fi, the other one's Fi plus 1. One is Fi, one is Fi plus 1. Let's go back. So when Pi, so let's say when P2 wants to eat, so you're gonna grab F2, also grab F3. So P2 gonna grab F2 and F2 plus 1, right? So that means, and the P1 gonna grab F1 and grab F1 plus 1. So this one gonna pick up the left fork, and this process gonna pick up the right fork. And now I also actually, for I plus 1, I also use the modular operation. Why I use the modular operation? Because when I equals 4, so when P4 wants to eat, you're going to pick up the left fork, which is F4. That's okay. Now, P4 going to pick up the right fork. The right fork is because it's 4. So already I equals 4, right? So when they pick up the right fork, which is Fi plus 1, that becomes F5, which does not make sense, right? Because there's no F5. So then you need to actually put the modular operation. So I plus 1 modulo 5. So when I plus 1 equals 5, you can actually replace it with F0. Does it make sense? Because we have to use the modular operation. Okay. Because it's a circular, right? So F0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So the left one is 4, the right one is 0. So this modular operation only applies when I plus 1 equals 5, then the index actually is back to 0. Okay. Same thing with this one here. So this is to pick up the left fork, pick up the right fork. The right fork could be 0. Now, if I is 3, the right one is I plus 1. So I equals 3, I plus 1 is 4. 4 modulo 5, it is still 4, right? It's still 4. Because modular operation is basically the division and get the remainder. So when 4 divided by 5, the quotient is 0, the remainder is 4. So it's actually still 4. But when 5 divided by 5, you got a quotient of 1, but you got a remainder 0. Okay. Just keep this in mind. So if you're not familiar with the modular operation, just keep that in mind. The modular operation is basically so like a 7 modular 4. So it's basically 7 divided by 4. And what is the remainder when 7 divided by 4?
3.
3. So 7 divided modulo 4 is 3. 7 modulo 7 is 0, right? So this is actually the solution we're going to implement. However, just keep that in mind. This solution may not be able to solve the deadlock issue because it's possible that each PI pick up the left one, and then they pick up their left one at exactly the same time. When they try to pick up their right one, none of the right one is there, right? So that's a deadlock situation. It's even it's unlikely, but it's possible. So that's the approach. Now, how to resolve this issue? So this code, the code I implement, okay. So that means each philosopher gonna run the same code, okay. Philosopher 0 gonna be execute P0. Philosopher 1 gonna execute P1. So the value I is different, but the code is actually they're identical. Now this code, this code may lead to deadlock. Okay, I don't know why it says before. Okay. Since all philosophers can pick up the left forks concurrently and then block independently on picking up the right forks. Okay. How can we avoid the deadlock? Any idea? Let me give you some hint. So we're gonna come back next time, okay? Next Tuesday. But let's actually think about two solutions. Several approaches exist to avoid the problem. Approach one, request both forks at the same time in the critical section. Okay, so that means they pick up both forks at the same time. Technically, it's possible, but when we try to write the program, you have to have some kind of order, right? But we can actually make sure that the two actually operation P going to be actually executed as a one, as a one piece, not. The other approach is one philosopher pick up the forks in the opposite order from all other philosophers. Because right now, the solution here allows people to pick up the left fork first and pick up the right fork next. So every philosopher is going to follow this order. Pick up the left first, pick up the right first, right second. So that's the reason why we suddenly have a scenario that all the philosophers try to pick up their actually left forks at the same time, and then try to pick up the right at the same time. They find out all the right forks are not there. Okay. Now, if we break that circle, just make the picking up order differently. One approach is like one of the philosophers pick up, the right first and the left second. Okay. Or they say the philosopher, like a philosopher 0, 2, 4, the even number, they pick up the right first, pick up the left second. And all the philosopher 1, 3, pick up the left first and the right second. So it's just try to break that circular thing. Okay. That's the solution. Then think about these two solutions. Okay. Do you think this is going to solve the problem? Now, the other solution, some people just, think about a very smart solution that just, how about we remove one of the philosopher? We don't allow 5 philosophers to sitting on the table. Just only 4 philosophers going to be available. Do you think this is going to solve the problem? Limited the number of philosophers. To 4. Okay. Think about this. Okay, we're gonna be back and talk about this. Okay, so I think that's pretty much all we're gonna talk about for the concurrent actually processes. Okay, so I think the next one we want to talk about, I can start. We don't have much time left, but we can start the discussions. That's the okay. So that's the next topic we're going to talk about. But in Zyborg, it just discussed various different solutions. But I think I mostly going to skip that section, the deadlock section. But I still going to discuss the concept of deadlock. Okay. Now, why deadlock happens? The deadlock basically happens when we have limited resources, but we have more processes. Now, these processes just while they're running, they all try to access the resources. If the process get the resources, they can continue to run. But if the process cannot get the resources, then the process is going to be stuck and waiting there until the resource is available, so the process can grab the resource and then continue. So if the resource is not available, the process is going to wait. Okay. Now, in the ideal world, so we have enough resources for every process, then we don't have any deadlock situation, right? So the deadlock will not be there. But the reality is, the resource is limited, always limited. Okay. So that's why we come up with the deadlock situation. Now, to resolve this deadlock situation, normally we use the resource allocation graph. It's called a resource allocation graph. Okay. The resource allocation graph use a couple of symbols. Now we use the processes. Okay. And then the process gonna be actually marked as circle. Okay. And the resource gonna be we use rectangle to represent the resources. And we also use a small circle inside the rectangle to represent the multiple units for the resource. For example, if we talk about a printer, and if there's only one printer, then there's only one resource, instance of the resource. Now, we talk about resource printer, but there are 3 printers are connected to the system. So that means you have 3 units, which means if process 1 requests for printer, process 1 can get the printer. Process 2 requests the printer. The process 2 doesn't have to wait because there are 3 printers. So if as far as one of the printers is available, the process can continue to grab the resources. Okay, so that's the multiple units. And so we use the allocation. The resource allocation are represented by edges directed from the resource to the process. That means this process is grabbing the resource, one instance of resource. So that means the resource is in the hand of this process. Maybe 1 unit of resources in the hand of the process. Now this is also use the arrow, but this time the arrow is actually from the process to the resource. That means it's request. Okay. This is actually means allocation. Okay. So process may request the resource, but the request may be granted or may be rejected, because if the resource requested, if there's no resources available, then the request are going to be rejected. So that means that the process need to wait. Now, if process requests for resource and the resource is available, that arrow going to change the direction. So the process going to be able to grab the resource. So you have an arrow, but you see the different direction, right? The different direction. Okay. Okay, I think time's up, so I'm not going to continue, but I just start the chapter 5, the module 2D. So you can actually start to look at the chapter 5 in Zybook, but I don't think I'm going to cover all the materials over here. So
can I speak to you after class?
Oh yeah, sure, no problem. Okay, so I think that's pretty much all for today. If you have any question, please you can ask now. Let me actually stop the recording.